Hello everyone. In this video, we are going to discuss two problems and their sub questions. So let's start with the problem one, where we have to, randomly set seed which are equal to 1, 2, 3, 4, and then generate a random variable x that has 10,000 continuous random uniform values between 5 and 15. And then also we have to generate a random variable y that has 10,000 random normal values with a mean of 10 and a standard deviation of 2.89. We are going to do this in R. So let's dive into the code. So firstly, we are just setting the random seed, then we are generating variable x and y, where for x we are keeping the mean, max, 5, 15 respectively. And for variable y, the mean is 10 and standard deviation as 2.89. We can see the first few values of our x and values for y. Moving on to next question, which is about probability, where we have to calculate a minimum the below probabilities through A to C. And we have to assume the small letter x is estimated as the median of x variable, and the small letter y is estimated as the median of y variable. So let's read the code. We are, creating x median and y variables, and we are calculating the first probability question, which basically is which says that the probability that the x is greater than small x, given that x is greater than small y, it's approximately 1. This suggests that if x is greater than small y, it is highly likely that x is also greater than small x. And we are getting the value as 1. For similarly, we are calculating the probability for P, which basically says that the probability that both x is greater than small x and y is greater than small y is approximately 0.2507. This implies a moderate likelihood of both events occurring simultaneously. And similarly, we are calculating probability for C, where it basically tells that the probability that x is less than small x, given that x is greater than y, is 0, as we are getting the value 0. But this basically indicates that if x is greater than small y, it is highly unlikely that x is less than small x. Moving forward with our next question, where we are trying to investigate whether the probability of this is equal to probability of this, where we are trying to build a table and evaluating the marginal and joint probabilities. So basically, the table of joint and marginal probabilities provides a comprehensive view of the relationship between x and y based on their magnitude. So again, we are calculating the marginal probabilities using the formula and joint probability. And we are building a table and the results are here. The calculator, we can see that, the values are like, almost similar to 0.2507 to 0.27. Which is basically that the calculated joint probability aligns very much close with the product of marginal probability, supporting the assumption of independence between x and y. Moving on to our next question, where we will see the independence holds by using Fisher exact test and chi-square test, and what is the difference between the two, which is the most appropriate. So let's talk about what is Fisher's exact test. So basically, this test provides an exact probability for the observed distribution and is particularly useful for small sample sizes. Whereas chi-square test, this test compares the observed distribution with the distribution expected under independence. It's applicable to larger samples and it's commonly used test for contingency tables. So here we are trying to, we are creating a contingency table. We are performing Fisher exact test and chi-square test, and we can see the results. It's 0.794, and the result for chi-square test, it's a little blur right now. Yeah, there we go. And the value is for chi-square test, p-value is 0.47949. We can see that the Fisher test and the chi-square test both yields p-value of approximately 0.749. The high p-value indicates that there is not enough evidence to reject the null hypothesis of independence between x and y. This aligns with the lack of significant association observed in the joint and marginal probabilities. Now, moving on to a problem 2, where we are going to work with Krabbage dataset. So we are going to download our initial libraries. We are just reading the data set and dividing our data set into test and train. This is the overview of our test data set, where we can see that there are 74,000 rows, 10 columns, and these are the column names. This is the overview of test data, where we have 49,000 rows and 9 columns. So now diving into our descriptive and inferential statistics. So basically, the univariate descriptive statistics provides us the key insights into central tendency and variability of the variables. So we can see that doing the summary, we can see that the mean, median, and third quantile, first quantile of each variables. This is basically a box plot for age, where we can see there are a few outliers for our gender variable. This is histogram for length, where our x-axis is length and frequency as a y-axis. We can see that it is little left screwed graph. And coming on to our scatter matrix, where we can see a scatter plot matrix. So basically, this examines, relationship between variables, helping to identify, if there are any potential patterns, where it's still a little blur. It's just taking some time to maybe, process it. Okay. Right. I think my internet have some issues. Oh, there we go. So this is our matrix. Here, basically, we are just creating a correlation matrix, which basically, provides valuable insights into the relationship between our key variables. Here, we are just taking our three, variables, which are length, diameter, and age. And these are the confidence intervals for a correlation, which we have taken. And, with the results, we can conclude that, length, diameter, and age shows, very strong positive correlation. The confidence intervals for these correlations are narrow, indicating precise estimates. The hypothesis testing for these correlation being 0 is strongly rejected. And here we are just, comparing the coefficient for each, pairs, like length and age, diameter, length. And, talking about the family error consideration, for this we can, try to apply Bonferroni method. This would basically adjust the significance level for multiple hypothesis tests, minimizing the risk of type 1 error. Coming on to linear algebra and correlation. So here we have to, invert our above correlation matrix and do some, calculations. So you just going through the code, we are just inverting the correlation matrix, then we are multiplying the correlation matrix by precision matrix. Here we are multiplying the precision matrix by correlation matrix. we are just decomposing the eigenvector and extracting the eigenvectors and values. So here are the results. So we can see that, it sheds lights on the interplay between the variables, the eigenvalues. um, So the these eigenvalues and eigenvectors contribute to understanding the structure of the data. And we can see the values here. Moving on to our next question, which is calculus-based probability and statistics. Just, we are we are doing the numeric columns from the data set, viewing it. These are the histogram for all our numerical data. We are just extracting the weight variable here and using mass package library here, and we are trying to fit exponential distribution with, and we can see and compare the diagram here, which is this one is our original and this is the exponential distribution. Basically, fitting an exponential distribution to a skewed variable allows for a more in-depth exploration of the data distribution. And further, we are, comparing it with the different percentiles, 5th and 95th. So basically, comparing the percentiles from empirical data and exponential distribution provides us insights into the goodness, of the fit. And here are the results in 5th and 95th percentile. Moving on to our modeling, segment, we are here just trying to fit the multiple regression model. And, this will be our initial multiple regression model, which basically provides a good baseline. And as we can see, our R-square is 0.53. So basically, it explains approximately 53% of the variability in age and demonstrates statistical significance. The inclusion of various predictors along with their interaction contributes to capturing the complexity of the relationship. And next step, we are just doing some feature engineering where we are just taking a square of weight variable and we are doing polynomial featuring, specifically the square term of weight. It basically enhances the model's flexibility. This nonlinear addition allows the model to capture curvature in the relationship between weight and age. The coefficient for weight squared is statistically significant, indicating its contribution to the predictive power of the model. And as we see the results, we can see that our intercept is 4.11. This estimates the average age when all the predictors are 0. And as we can see that the height, weight, and shell weight and diameter have a good positive coefficients, and increase in this variables is associated with increase in the predicted age. And we can also see that there is negative coefficients between length, shucked weight, viscera weight, and weight squared, which basically tells us that an increase in these variables is associated with a decrease in predicted age. And as we can say that all coefficients are highly significant since the p-value is less than 0.001, indicating that each predictor contributes significantly to explaining the variation in the age. And here we can see that our R-square is 0.54, which basically indicates that the model explains approximately 54.6% of the variability in the age, and our adjusted R-square is 0.546. It penalizes the model for including irrelevant, basically, predictors, eliminating the insignificant variables. And also we can see that our F value is 1.113 and so on, with a highly significant p-value, suggesting that the model as a whole is statistically significant. So this is pretty much about this video, and I also have uploaded my project on Kaggle, and this is my user ID. Go check it out. Thank you so much.